Very good afternoon. Today we will continue our discussion related to the differentiation of the energy carriers in different media and their attributes that we were looking at. So, we will add on to the attribute where we stopped yesterday, that was the type of particles. We classified for example, phonons which are responsible for heat conduction in semiconductors and dielectrics. So, they are essentially described by the statistical distribution function called the Bose-Einstein distribution function, okay, and therefore, they are called bosons. And what is the therefore, nature of this particle? So, I mean when we are also talking about the corresponding particle type, we need to understand their nature. So, let us also write down the classification based on the nature of particle. So, as I talked about, you should know that in statistical thermodynamics, these different particles are classified. For example, the bosons have a characteristics that they are indistinguishable. And that means you cannot distinguish the carriers themselves from each other, they all look alike, and there is no limit to any number of particles or you cannot fix the number of particles which can occupy a quantum state, and therefore, you can say that any number of particles can occupy a given quantum state or energy state. A quantum state is nothing but an energy level or discrete energy level. We will see all those things in a short while, or a quantum state. Okay. So, this is maybe you can say something like integer multiples of h nu, okay, where n can be 1, 2, 3 and so on. So, these are discrete energy levels, and at each energy level there is no restriction on the number of bosons that can occupy. The same thing follows also for the photons, which are also coming under the boson category. So, they are also having the same as phonons. And when we look at electrons, for example, they are described by Fermi-Dirac distribution function, and the nature of these particles is they are also indistinguishable. However, you have a problem that for a given spin, okay, you have a plus half and minus half spin quantum states. So, only one electron can occupy a particular spin quantum state. You cannot have more than one. If you have a plus half spin, that electron can occupy that quantum state, and minus half spin can occupy the other one, and so on. So, this has to obey, therefore, Pauli's exclusion principle in terms of occupation of the quantum states. Because of the spin, electrons possess this unique characteristic. Okay. So, therefore, only one electron can occupy a given quantum state, okay, plus half quantum state or minus half quantum state, depending on the integer spin. Okay. Now, the molecules, coming to the molecules, now molecules are real atoms. So, you can actually distinguish between the molecules. Okay. A molecule of a particular gas will be different from another gas, and again so therefore, these are coming under the nature of distinguishable particles. And again, just like you have your bosons, you can have any number of molecules can occupy an energy level. Okay. However, these are governed by the distribution function called the Maxwell-Boltzmann, which is not a quantum mechanical distribution function, but it is a classical distribution function. That means the energy levels are not quantized or discrete like the case of Bose-Einstein or Fermi-Dirac. The Maxwell-Boltzmann has continuous energy levels. We will see all those things, we will understand it gradually, but this is a very important way of classifying the energy carriers. So, let us also write down the corresponding distribution function now. We will derive these when we do this under statistical thermodynamics. So, equilibrium distribution or occupancy function. Okay. So, this is your F equilibrium as a function of the energy of the particle. So, this is what we derive from the statistical thermodynamics, describing the equilibrium, what is the distribution of the particles at a given energy level under equilibrium conditions. So, if you look at the Bose-Einstein distribution function, you can write this as 1 over exponential E by kBT, where E is the energy. Now, in the case of phonons and photons, this energy is nothing but h nu, E is equal to h nu, Planck's law. Okay. You can also write this h nu in terms of modified Planck's constant h cross as h cross into omega, the angular frequency. Okay. So, you can multiply and divide by 2 pi. So, 2 pi nu will be the angular frequency omega. So, h nu by the Boltzmann constant kb times T, the denominator, entire thing minus 1. Okay. So, you have 1 by exponential h nu h cross omega by kBT minus 1 is the equilibrium distribution function given by Bose-Einstein, and the same thing holds for also the photons. Okay. And when we look at the Fermi-Dirac distribution function, structurally it looks little bit similar, but you write this as the energy of the electron or the energy of that particular quantum state which the electron occupies, minus this is called the Fermi energy nu. Sometimes people use this as E subscript f, which is the kind of a reference energy level. Okay. So, divided by kBT. Now, the major differentiator between the Bose-Einstein and Fermi-Dirac is, instead of minus 1, there is a plus 1 here. Okay. So, otherwise structurally it looks very similar. And then for the molecules which are given by the Maxwell-Boltzmann distribution function, you can write this as 1 by exponential. Now, the energy E for the case of molecule will be what? Primarily kinetic energy. So, you can write this as half mv square or mc square or mv square, because c you might confuse the speed of light. So, v square is actually absolute velocity, which includes speed in all the 3 directions, because the molecule can actually collide with motion in all the 3 directions, Vx, Vy, Vz. So, therefore, you can actually write this as Vx square plus Vy square plus Vz square divided by 2, okay, and you also have the kBT. So, this is your Maxwell-Boltzmann distribution function. Although they look very similar, we should understand that what is classical about the Maxwell-Boltzmann distribution is that Vx, Vy, Vz are speeds and they are continuous, okay, minus infinity to plus infinity, whereas h bar omega energy of quantum state, they are all discrete. For example, although this says h bar omega, they are n into h bar omega. So, they are discrete levels of energy 1, 2, 3, 4 depending on that. Okay. So, that is why the Maxwell-Boltzmann distribution is called a classical distribution function, whereas the others are quantum mechanical distribution functions. They exhibit this discrete nature. So, what is the corresponding frequency or energy range? Now, when you talk about phonons, what will be the maximum energy till the phonons can possess? Is it 0 to infinity? No. Okay, whereas for the molecules it can have 0 to infinity. Similarly, for the electrons it can occupy energy states all the way from 0 to infinity depending on the temperature, okay, and depending on the material. Your photons also can have energy levels from 0 to infinity, but your phonons being crystal, so there is a maximum frequency till which the phonon can be present, and therefore, the energy is limited by an upper cutoff. So, this is called as d by cutoff limit. Okay. So, this d by cutoff is basically dictated by the solid state physics for which we describe the phonon dynamics. So, the material will dictate what can be the maximum possible frequency that a phonon can take, and this is called the d by limit, right. And let us also look at the order of magnitude of the velocities. Okay, this is in meter second inverse. What is the order of magnitude of phonon velocity? This is the speed of sound in a given lattice. So, usually this acoustic sound is of the order of 10 power 3 meters per second, maybe few thousands. Usually in crystals the speed of sound is quite high, okay. So, of the order of thousands, it could be even 10,000 sometimes, okay, meters per second. And now, when it comes to electrons, what do you think will be the speed of these electrons, free electrons? Of the order of 10 power 6 million meters per second, okay. And when you talk about molecules, gas molecules for example, it should be of the order of few hundreds of meters per second, right. So, it is 10 to the power 2. And what about the speed of light? 10 power 8. So, each of these energy carrier is also limited by the corresponding speeds that they can take. The order of magnitude is quite different, and we will also express their mean free path, which is a very important characteristic to understand subcontinuum transport. Okay. So, the mean free path of phonons typically are ranging between 10 to 100 nanometers. So, if you are describing these lattice vibrations by representing them as particles, so the separation, the average distance between two of these phonons before they collide will be traveling around 10 to 100 nanometers distance. So, therefore, if you are having a device length scale which is lesser than 100 nanometers, then you are definitely falling in the subcontinuum regime, right. So, if you are talking about electrons, they also possess a similar mean free path as the phonons, 10 to 100 nanometers, whereas the molecules can have even lesser mean free path, okay, especially if you are talking about gases, they can have very small values of mean free path close to even 1 nanometer. In liquids it can go to order of 100 nanometers. Okay. In fact, I think yeah, so you have to be very careful with the order of mean free path that you are talking about. Sorry, it should be the other way. So, for the gases it should be of the order of 100 nanometers, I am sorry, and liquids it should be around 1 nanometer. Okay. So, the chances of therefore finding subcontinuum with gases is very high. If you are having a 100 nanometer channel and fill it with gas, you are already in the subcontinuum level, whereas with liquid same dimensions of channel you will be still in the macro scale regime. And when it comes to photon transport, so they also have similar starting value as the phonon and electron, but the ending value can be very large, okay, depending on the kind of electromagnetic wave, which spectrum, part of the spectrum you are in. Okay. So, therefore, you have different length scales associated with each of these energy carriers. The other length scale that is required to understand the quantum mechanical aspects, that is your wavelength. Okay. So, the wavelength of phonons is of the order of 1 nanometer. So, now if you are reducing your device dimension to the order of 1 nanometer, now you will start experiencing wave effects, because yeah.
How will photons have mean free?
The photons mean free path is, you can approximate them to be similar to the wavelengths that your electromagnetic waves are experiencing. Okay, if a wavelength is of the order of kilometers, you can, if you represent them with photons, so that is the average separation between the photons before they interact, something of that sort. Okay. So, similarly, yeah, I mean in photons it is not very explicit like the way phonons, because they are all in medium, the other three, whereas electromagnetic waves they are operating in vacuum. So, how do you explicitly, but here it is the scale of similar to the scale of the wavelength. In fact, that is why now when I explicitly put wavelength, now I am going to say that for the case of photons, again the wavelength scale will be similar as the mean free path. Okay. So, you are just looking at the wavelength and your mean free path is also of the same order, whereas they are quite different for the other energy carriers. If you are looking at electrons, for example, they can vary between 10 to 50 nanometers, and again for molecules it can be of the order of 1 nanometer. Right. So, therefore, things are not so simple. I mean, when you say Knudsen number of 10, it depends on the kind of, first the kind of media that you are talking about, and again you have to be careful whether this approaches the wavelength. If so, then the quantum wave effects will also start appearing, and you have to be dealing with those aspects as well. Okay. So, overall this is a very elaborate classification of the energy carriers. So, I think by now you should fairly understand how these energy carriers appear, to us. I mean, out of these phonons and photons are virtual particles. Okay. So, now since we are talking about the microscopic picture, okay, we talked about approximating the lattice vibration with phonon gas and so on, similarly electron gas, okay, and we have talked about their characteristics. So, the next question will be talking about how much energy or momentum can each of these energy carriers possess. That will be the next question, right. So, each of these particles at a microscale level will be governed by the corresponding momentum or energy they possess. So, what is it? How is it classified? So, let us also give some kind of classification of that. Okay. So, when we say energy, again now we have to be a little bit more explicit in micro scale, that we can talk about either a classical energy like your kinetic energy when you are looking at the particle nature, or if you are talking about the wave nature, that is very small dimensions where the wavelength becomes significant order as the characteristic dimension, then the wave effects will now bring in quantum mechanical things into picture. So, therefore, if you are talking about particle nature, you are having your classical mechanics to study the energy possessed by the particular energy carrier, right. If you are talking about the wave aspects, then you have quantum mechanics to understand the energy possessed by these carriers. So, therefore, we will classify this into the energy in the quantum mechanic regime and in the classical regime. Now, again we have different modes of energy. Now, when you look at particle, for example, what are all the different kinds of energy this particle can possess? So, for example, atoms, a single atom, monoatomic structure. So, what can one? It can have very good translational energy. Okay. Then, so for a single atomic substance, monoatomic gases for example, can there be rotational energy? Cannot be. For a diatomic molecule, then there can be rotational energy also. So, you can talk about rotational energy, and then what about also. So, you have for example, the picture of a phonon, which is nothing but two atoms connected by a spring. You have vibrational energy, same thing with interatomic potential between molecules and so on. So, you also have vibrational energy. So, these are the three major microscopic energies which added together will decide what is the average energy, total energy possessed by the particle. Okay. So, that will contribute to on the macro scale internal energy. Internal energy on the macro scale is nothing but the sum of all these three microscopic energies. Okay. Now, these can be there both from the classical mechanical perspective as well as quantum mechanical perspective, depending on what scales you are looking at. Okay. Now, when you are talking about, for example, the translational energy from classical mechanical perspective, what is the translational energy? Half mv square. You have a particle with a velocity v, and therefore, the corresponding momentum is mv and the energy is half mv square. So, if you write this in terms of momentum, so let us say the momentum p is equal to m times v. So, how can we write this in terms of p? P square by 2m. Right. Now, what we will do here is quickly switch on suddenly from the particle to the wave nature. So, there is a relationship between the momentum and the wave vector if you look at the wave nature. So, that is given by modified Planck's constant time k, where k is nothing but wave vector related to the wavelength lambda, 2 pi by lambda. So, therefore, if you substitute this into the relation h times h cross times k, your p will be nothing but p by h by lambda, right. So, this wavelength lambda, which is h by p, is called the de Broglie wavelength. Okay, so, this says that the wavelength is related to the momentum of particular wave. Okay. So, you can easily switch between toggle between the particle picture, wave picture whenever. So, p square by 2 m is from the particle picture. In the equivalent wave picture, if you are substituting for p as h cross times k, modified Planck's constant times k. So, this will be h cross square k square by 2 m. Okay, now, the k is wave vector. So, it is a vector in space, and therefore, when you say k square, it is the square of the magnitude of the wave vector. Okay, so, therefore, we can write this as k x square plus k y square plus k z square. Okay. But here this is classical mechanics. So, these are continuous waves. So, therefore, the wave vector k in the x direction k x, k y, k z are all continuous. So, added together they will contribute to the translational energy. Now, in the quantum mechanics, how do we find this translational energy? So, this is done by solving the Schrodinger's wave equation, and the typical system that you will consider is called the particle in a box. This is one of the simplest systems to which Schrodinger's equation can be solved easily, analytical solution is possible. Okay. So, you have what is called as a quantum well, okay, where you have a single particle like this, and within the well you have a certain potential, and outside the well this particle cannot escape because the potential will be infinite outside. So, it cannot escape from that well. Okay. Within the well the particle has a certain potential energy u, okay, but it cannot come out of that well. So, it is always confined to that well. Okay. So, this is called particle in a box or quantum well. Quantum well is 1D. If you make it 2 dimensional, it becomes a box. Okay. It has confinement in both directions, left, right, top, bottom also. Okay. So, in this case, when we solve this Schrodinger's equation, which we will do next week, you will end up getting expression for the energy. Now, in the Schrodinger, so how do we find energy in quantum mechanical states? So, this energy turns out to be the eigenvalue of the Schrodinger's equation. Okay. When we, so Schrodinger's equation is a partial differential equation, we have to solve that by method of separation of variables. We separate that into an ODE, which is a function of space, and another which is a function of time, and the equation, the ODE is a function of space, will have a certain eigenvalue, and that eigenvalue will give you the energy. And if you calculate that, it turns out to be very similar to what we have for the classical particle, except the fact that the k now becomes discrete energy states. Okay, you have, for example, if you are talking about kx, you can write this as some L pi by d, where L is an integer. It can go from 1, 2, 3, 0, 1, 2, 3, 4 and so on, infinite number of energy states. Similarly, in the y direction it will be another integer m pi by d, and in the z direction it could be n pi by d. So, now this is where the quantum mechanical energies are different from the classical energy. Classical energies are continuous, whereas quantum mechanics, what it is doing, the particle when you put it in a box, it is confined, and now this confinement, because of the wave nature, okay, we are talking about the box which is of the order of nanometers, 1 nanometer, 2 nanometer. So, the wave nature is going to break this continuous wave into discrete energy levels. So, this is called quantum confinement. Okay, so, this d is basically the width of this particular well.
So, what is the physical significance of this wave vector? Why do you represent it in terms of wave vector?
Generally, I mean in physics, especially quantum mechanics, all these waves possess certain momentum and energy, and they are all functions of the wave vector. This is how I have given this. So, this is the fundamental expression which relates the momentum. Similarly, energy also can be related. We have related also now energy with respect to the wave vector. Momentum is also related to the wave vector. So, you want to understand what is physically the wave vector. So, for that we will take few more classes. Down the line I will explain the wave vector space. Just like you have a physical coordinate space x, y and z, there is a space where you can talk about velocities, momentum space, Vx, Vy, Vz. Analogous to that is your wave vector space, kx, ky, kz, because these wave vectors are nothing but related to your momentum, particle momentum. So, therefore, you can transform your momentum space into a wave vector space. The particles also possess velocities in each direction. So, they can be plotted on that map Vx, Vy, Vz map, and they have a certain vector which is pointing in the direction of V vector. The same way is the k vector. So, in quantum mechanics what we find is basically these energy levels are no more continuous, but they get discretized because of the quantum confinement. You are confining these waves to a certain dimension, and because of that they split up. There is no single value of energy, but there are multiple levels, there are discrete levels also. Okay. So, this is where the quantum effects, what people say quantum effects, start appearing. So, all the wave vectors now become discrete integer multiples of pi by d. Okay. But however, the gross expression here looks structurally similar to the classical mechanical expression. Now, if you talk about rotational energy, in the classical mechanical perspective, how do you calculate rotational energy? You replace your mass with moment of inertia and your linear velocity with your angular velocity. Okay. So, as simple as that. Now, in quantum mechanics we will solve the Schrodinger's equation for the simplest rotational atom, that is the hydrogen atom. The two atoms and they are rotating. Okay. So, for that we solve the Schrodinger's equation to describe the energy contained in the rotational due to rotation, and we see once again they are quantized, and that energy is again a discrete energy which is given as h into capital B into L plus 1. Okay. So, where these L is the integer 0, 1, so on infinite levels. Okay. So, this B here should be function of the moment of inertia I. Okay. And then these become quantized, and this quantization is what? Nothing but discrete levels, splitting of the energy into discrete levels, and that is given by this integer L 0, 1 to infinity. Okay. This also we will show under quantum mechanics. Now, when we go to vibrational energy, I will first if you look at the vibrational energy in the classical perspective, the simplest way to look at it is the spring mass system. Okay, the atom can be assumed to be a mass, and then the forces of attraction between the atoms can be assumed to be having a spring constant like nature. We are not considering any damping now, we will have only a spring constant and a mass. So, therefore, if you write down the equation of motion for this spring mass system. So, let us say initially this is at some level x equal to 0, and then you from this level you disturb it, you pull it and let it go. Okay. So, the displacement is basically x is a function of time. Okay. It depends on the amount of mass that you have and also this spring constant. Okay. So, you want to track the displacement as a function of time, the velocity as a function of time. So, therefore, we solve the equation for this particular system. So, you have mass into acceleration is equal to minus kx. This is where k is your spring constant. So, if you solve this with the condition that at t equal to 0, so you have the fact that your initial velocity is 0. Okay, you start from a resting state and then you let it go. So, therefore, dx by dt is equal to 0. So, how many conditions you need? You need two conditions. So, one is dx by dt, and what about x? Also at t equal to 0, x equal to 0. So, what is the solution to this particular expression? We can write this as d square x by dt square plus k by m, and I can represent this k by m, I can use omega to describe square root of k by m. So, we will hold on to this, we have k by m into x is equal to 0. So, the solution to this will be basically as a function of sine and cosine, right. So, therefore, we have x of t will be c1 cos square root of k by m. Now, we will replace that with omega plus c2 sin omega t. And therefore, the velocity dx by dt, if you differentiate it, will be minus c1 omega sin omega t plus omega c2 into cos omega t. So, now you please apply the initial conditions x equal to 0 and dx by dt equal to 0, find out the constants c1 and c2. So, the condition that dx by dt is 0 should give you what? C2 should be 0, right, and therefore, the other condition that x equal to 0 at t equal to 0, if you apply that, C1 cannot be 0, otherwise the solution becomes trivial. So, therefore, cos omega t should be 0. Okay. So, this will give you the corresponding value of omega. So, that should be expressed, just a moment. So, we do not have to worry about that right now. I think for calculating the energy, all we need is only the dx by dt, okay, only the velocity is required. So, therefore, C2 is equal to 0. So, therefore, our velocity of motion dx by dt is given by minus C1 omega sin omega t. Okay. So, and therefore, your x is just C1 cos omega t. So, therefore, the total energy in this case will be summation of your kinetic energy plus your potential energy. So, the kinetic energy is the component of half mv square, and potential energy is due to the spring constant half kx square. Okay. So, therefore, the total vibrational energy that we are talking about here consists of both the kinetic and the potential energies together. Okay. So, if you substitute for V into this expression and x into this, so you have therefore C1 square omega square sin square omega t plus half into k can be now again written in terms of omega and m, as k square should be omega times m. So, you have omega times m, and again m you can write in terms of again you can express k by m, and therefore, m can be written as k by omega square. So, this should be C1 square omega square into cos square omega t. So, essentially this should come up to half C1 square omega square, right. So, this is your total energy. Okay. So, this is therefore your vibrational energy that we wanted to fill up. So, that consists of the summation of your kinetic and your potential energy, that is your half mv square plus half kx square. For the case of spring, assumption of a equivalent spring mass system, which is a linear system, this turns out to be half of m C1 square omega square, right. Maybe I will just give you a couple of minutes to work it and check again. For some of you are doing it slowly. I will go back to this point, you make sure that you work out all the steps. I think I missed a m here. Yeah, you are right. That is what I was also thinking here. So, there should be an m here, m C1 square omega square, because the energy cannot be independent of mass, right. Okay. Here I have written correctly, good. Similarly, in the quantum mechanical vibrational energy, we also consider a similar problem, spring mass problem, but we solve the Schrodinger's equation for that. And so, in that case we again have a quantized vibrational energy level, and the energy for the vibration is given as h nu times n plus half, where your nu is nothing but 1 by 2 pi square root of k by m, and your n can take the value 0, 1, 2, so on. Okay. So, this is some integer multiples of h nu, but instead of an integer multiple we have n plus half coming into this picture, and n is, these are at discrete levels. Okay, when we solve the Schrodinger's equation, then you will understand why this is coming this way. Okay. But yeah, I mean there, since E is the eigen value, so you have these eigen value of the Schrodinger's equation, this is coming as function of h nu, okay, where nu is 1 by 2 pi square root of k by m. So, here also if you take the eigen value, you find the eigen value from this expression. So, you should be able to come to a similar expression, right, correct. So, you have cos, maybe you can just try this out yourself here, the classical, when we are doing the classical energy computation. So, putting the other initial condition tells you that your cos omega t is equal to 0. So, that means omega t should be is it n pi by 2? How about 2 n plus 1? 2 n plus 1 pi by 2. So, in this case you are saying that your omega is equal to, omega t is basically 2 n plus 1 pi by 2. Okay. Okay. So, these are the eigen values, right, for n is equal to 0, 1, 2, 3 and so on. Okay. Similarly, for the Schrodinger's equation, the eigen values are giving the vibrational energy levels here, h nu into n plus half. Okay. So, this is what we will do in the next few classes. We will go into the quantum mechanics, solve the Schrodinger's equation, and we will see how the eigen values are obtained, and then how do we actually derive these particular expressions, right. So, what I would like to do is now stop here. So, we have, I think, had a lot of classes for introduction. I think we spent couple of weeks only on the introduction part, but it gives a very good foundation. Now, you are able to understand different kinds of energy carriers in different media and their characteristics, and also you should be able to appreciate that energy when we talk about as a microscopic basis, and also in microscale there can be energy associated with the particle based picture as well as quantum mechanical picture. Okay. So, the next week we will go into the quantum mechanics to derive these energy expressions from Schrodinger's equation. Okay. So, I will do a little bit basic, at the same time I will also go a little bit fast. So, you can also do your reading parallelly on these topics. I will try to make it so that people who do not have any understanding of quantum mechanics can pick up. So, it will be mostly conceptual. I will also try to parallelly derive the expressions. Okay. So, thank you.